Mohammed Jahangir. I'm a radar researcher by background. I have spent many years in MOD, defense sales, and also recently I was working for Palace, working on this ground-based radar for drone surveillance. Some of that technology we have brought to Birmingham here to look at other aspects of radar without them to bring touch in presentation today. But my main focus is to see how radar could be worked in a challenging environment. Multi-static, multi-network is a key focus of my research. I'll let Darren introduce himself, and then we'll sort of carry on with the presentation.
Hello, I'm Darren Griffiths. Thanks as well for everyone for hosting this. It's very happy to be here to give the talk. So I'm a fourth year PhD student, also working on quantum enabled network.
It's like considering what they teach, but in terms of like.
And my focus is more on mostly on network radar synchronization using low phase noise oscillators.
Great. Okay. All right. Okay. So the title today is we're going to talk about synchronization of L-band strain radar with GPS-specific oscillators. But in the back of this, I'm going to explain the facility we have, which is as I mentioned. We're looking at modifying radar with different type of oscillators, and the particular oscillator we're interested in are coming from the field of physics with the photonics and specifically quantum enabled, because we're highly interested in the some of the capabilities of those talking about the short-term stability and the long-term stability, and how that can improve the noise characteristics of radar and how they can improve the synchronization. So with that note, I'm just going to see. Okay, so this is the kind of brief overview of the presentation. We're going to talk about the network radar setup, the motivation, why we're interested in looking at quantum enabled radar, what actually means when you say quantum enabled, and then we talk about the facility which is set up, which is an L-band strain radar. It's a commercial radar, but we brought it into a research arena. We'll show how we set it up and what we hope to do with it. We're going to talk about some of the initial work we've done in interfacing this, or modifying the radar front end, which allows us to change its capability. And we actually going to talk about some of the benchmarking we need to do. And one of the ways we are trying to sort of baseline the capability, which we can then assess how we're changing this radar in terms of the oscillator characteristics, and how we can then assess when the radar be used as a network. Darren is going to talk about this work that you've done, and thanks to Piers and Matt for giving us the opportunity to test a particular type of oscillator, conventional oscillator. Because our interest is to look at radar in its conventional form, with the conventional capability, and what does this new capability, which are being driven by the development in quantum, can bring to the radar. So very keen on how we can do this baselining, and there we use conventional oscillators, which are discipline GPS, how the radar can operate as a network. Show some results today, which are going to go through in the second half of this presentation. And we're going to conclude the summary and overview of where we think then we can take this capability forward. Okay. So with that note, I'm going to start with a very basic concept of what we are trying to do with the radar. So here we're looking at moving targets. So we're looking at the Doppler we're getting from these targets. So this is the pulse radar. So what we'll get is a coherent system. So we can actually measure the Doppler of the target. So depending on the targets, what the velocity is, we will see them spread out in Doppler in terms of the frequencies, and they will have different strengths depending on the size of targets. So small target like drone will have quite weak spectrum. And if the radar is designed well, then against the thermal background noise, we should be able to detect the targets which the radar is designed for. But when we have a real environment, we have a clutter, we have strong return, and what are we finding that the phase noise in the oscillator is beginning to impact on what the effect of the ground clutter is going to be on the detection of this time. Because the ground return, which might just sit in the zero Doppler, begins to have the spreading out because of the phase noise. And the stronger the clutter is, the worse this degradation of performance in terms of effects. And here we're showing a map in the sort of some of the main that we started doing in Birmingham. So how does this cluster strength vary as a location? And the stronger the clutter is, that's where this effect of the phase noise of the oscillator is going to impact on the performance. That's what we're interested in, one aspect. And we're saying that if you have an oscillator with a low phase noise, fundamentally you can begin to take away this effect of the environment on the performance of it and bring the radar comes back to what an ideal situation. So the radar will work best in a thermal noise environment. There is no pattern, just got the target, and that's where you got the maximum SNR as designed by the radar in terms of its power quantity. But we don't get achieve that in reality, and this is the question: can we actually do something more in terms of the radar design, which can make sure that the radar is the least affected by the environment? And here we talk about strong static pressure affecting the detectability of small, slow-moving targets. So in terms of our setup there, what we are saying is a bit of the radar front end, which we want to look at, is right at the heart of it. So here's a typical front end radar. We have oscillator, you've got an up converter here. In this case, it's a pulse system, so it's a modulator, and then you have a filter and an amplifier that transmits on the receive side. It's in reverse here. You have a mixer with that local oscillator, which gives you signal baseband, which you can size it. And what we are looking at is that the oscillator, which is quite a local oscillator reference, we replace that with an oscillator which has a much better quality in terms of its frequency stability and its phase noise characteristics. Okay, so kind of I'm just highlighting those aspects there. So the benefit is that if we have lowered the oscillator phase noise, in the monosensor we have a much lower phase noise. In a bistatic setup, that's even more pronounced because you don't have any self-cancellation. So if there is a higher phase noise here, we will actually see that coming through our the noise floor of the bistatic. And then Darren is going to show some results where that becomes quite visible. Is that, and then having an absolutely low phase noise is quite crucial there. But we're also looking at that in a synchronization, the stability between the clocks, where the relative frequency is not drifting, can be shown to maintain the frequencies. So in one sense, we're looking at any oscillator which is low phase noise and higher stability, and part of our remit is look at the system and testing it for all these different configurations. And this is why some of the work we did with UCL, high performance GPS, so it's part of that understanding of that performance. But ultimately, we envisage that the solution is going to come from photonics-based systems, which are then eventually disciplined to quantum clocks. And here we have a challenge in how these devices, optical devices, work at terahertz, how we bring that down to tens of megahertz, where typically radar system works. And that's where we have a solution, which is our physics colleagues have proposed, which is using a device called a microwave photonics generator. We can take optical signals through a solution called frequency comp. I'm not going to go into much detail on that today, but happy to talk about it offline if you have more interest in how that optical to RF conversion is going. But we'll show you some of the example of the setup we have, which we're achieving that conversion. And that allows us to now tap into this new regime of oscillator, which we believe have characteristics which may be of interest to radar. And that's the part of what we do is that viable to get radar operating on these new oscillators, and if so, how much difference in capability we can be able to achieve. And what else in the radar design we need to alter to make sure that improved performance of the oscillator carries through the radar content. So, that's kind of our view of motivation. We said, so we want to have radar where we have the ability to connect with the So at Birmingham, we have come to this particular solution where we actually taken an L-band commercial radar developed by Thales. It's a company that I used to work for, so I know these radar quite well. Birmingham team decided to make those as part of the test spec. And these are large radars which have to go on a sort of fixed location. So we ended up putting on rooftops of a campus building. We managed to secure a few locations, which wasn't easy feat. But and we had to have some engineering work because these systems come with a cabin which houses all the server systems, and the radar itself here, which is on top of this cabin, weighs about a ton. And the whole setup is about 3 tons there. So we had to have steelworks put in, but we managed to do that. The first radar was installed right in the period of COVID lockdown. So that was on the November in 2020, when we were the only one on campus because everybody else was staying at home, but we were allowed permission to come and install them. And then a year later, we had a second radar set. So these are L-band radar. So they have a broad beam on transmit, but they have now an array of receivers. So they have 64 channels. and this they are fully digitized and they can form electronic beamforming. And this radar has been designed to look for small targets. So the company had marketed this for selling to airports for surveillance of drones against intrusion, and that was very interesting because this system here is able to look at small targets. It's designed to do very long integration. So typically it will integrate about 4,000 pulses. And that's very interesting because that's the longer the integration, the more the phase noise effects manifest in the processing. And we want to actually understand how does that phase noise manifestation is happening, how does that can be addressed through the changes in processing. So that's the physical setup here. And this system is working here. We can work it 24/7 here. It's actually can actually look at a azimuth axis of 90 degrees. So we're now looking at our Birmingham cityscape. We're looking toward the city centre and some residential area. We can look out to 5 kilometers. And this is just a screenshot of the live output of the radar here, where we get a detection 4 times a second update. And we can form tracks in real time. Here's the processing with the radar manufacturers, which show live output of targets. We have a 3D view, so we can actually see targets up to a height of 1,000 kilometers, and we can actually then now set up the raw data for this one. So we can go back to the raw data, look at scenario characteristics, look at pattern maps, and we can then relate it back to the processing, how well the detection works, how well the tracking works. We are interested in drone surveillance, so we have found a few locations here. We're going to talk about that, where we have actually be able to locate these targets, test targets, and we can assess the system in the system. What we have actually done is, as said here, we have an ability to get the raw IQ data. So this is all 64 channels. So we can form the beams in software, and we can form it in all directions. So we are looking in every direction all at the same time. So we get the continuous development in any direction. So we can. Our default is to integrate for quarter of a second, but the work we'll be doing is we have been look at integration of tens of seconds. And we look at what the coherent gain. That's going to be quite interesting for us to examine that in order to look at the effect of synchronization and coherency. But here, what I'm showing is that we are looking at quite dense clutter. So the yellow is some strong return we're getting. One of the radars, which is called radar 1, we're looking towards the city centre. We've got quite bright buildings in our live buildings of field of use. We get quite strong clutter returns. The other radar is looking a little bit more toward the rural area, but there's still a few regions of very strong clutter, which is of interest for this assessment about the background statistics. And then we got the whole field of view check the assessment of the radar against targets. Just moving on, so we've got this test bed here. We can operate in a busy environment. We can operate 24 hours. We have raw data here. And how we're looking to change. So we want to do the benchmark. Early work was that didn't make any changes. Looked at this radar, did measurements as it is. And then we're looking to see how we can change the oscillators. Early on, we said we want to take the conventional oscillator, which is oscillator with alternate oscillator. So our main goal here is to let's see if I can get this mouse here, to bring in this device here, which is a microwave photonics generator. It's a commercially available device built by a company in Germany called Menlo, and they can take an optical signal. So this radar, this unit has got a built-in laser cavity, which provides a reference signal, which can then be converted down through a solution called frequency cone, which can produce several harmonics and low frequencies, starting from tens of gigahertz going all the way to tens of megahertz. And we can then take the output, which is at our local reference frequency for the radar, and then feed that into the radar here. That itself there is a good starting point because these optical lasers here have a very low phase noise, very long stability. We have both these units installed in both of these radars. They need to be co-located because the optical to RF conversion is done local to the radar. But then we can actually discipline this device through other systems. So in this setup here, if you go right to the left here, we have the strontium clock. This is the work we've done in the physics team here, where there is a highly stable clock which can then discipline this laser here. That laser in the lab here then can signal sent up to the radar through a fiber link. That fiber link needs to be carefully stabilized. That's the work which the colleagues are doing here. But that means that then we have a clock here which can act as a master clock and discipline one or more radars simultaneously. And that's where we want to go with this working. So this is kind of our vision here, that we have two radars in this setup. We can give us a network. We have now a manual microwave generator unit, which is installed in both of the radar, which can give us a local reference, which is highly stable and no phase noise. And then later on, when we have a sponsoring clock, that can actually send a master signal to each of these radars. But we also have a hybrid solution where one of the manual can act as a master, and we can then have a clock which can distribute two radars. And we have a fiber link connecting both the radars and also the radars to the ladder. So that's physical setup is in place there, and all the time we will bring different oscillators and different clocks online and to be operating through the radar. But what I want to talk today about is how we begin to connect the radar. What are the things that we have to pay attention to be able to connect these oscillators, and how we begin to benchmark these oscillators so that we can understand or predict what we believe the radar output of these systems is going to be like. So if I show you here, so on the left here, we have the device in the radar, which we're calling the TWIG, time waveform generation, which is a device which produces a carry frequency, and that carry frequency is generated through a local Griffiths oscillator. And that actually does a phase lock loop here with that kind of converts to L band here. And what we're doing here is we rather than have an internally built-in local oscillator, we are then actually finding these external devices here. And what we're saying here is that in the first instance here, we're just putting a simple safety measure here, a buffer here, so that if you're taking the sine wave, which is a local oscillator, we can then convert that to a square wave, because the time device in the radar likes to work on a square wave, because that gives a clean clock here. This is up in the radar here, and we need our oscillator to be in the cabin here, so we need to put in a long cable, and then in the radar cabin we are putting a switch here where we can connect different oscillations, and this operation can all be then managed remotely here. And what we are doing here is that we can then bring in different oscillators online and begin to look at the characters at the output of oscillator frequency, and also at the frequency once we've done this conversion here. So this is, we started off looking at this assessment. So we come up with this clock transfer frequency, that we have an oscillator, we can connect it to a switch, you can then connect it to a buffer, which can then take a sine into square wave and then feed into it. We had one of these TWIG devices available as a spare, so we could actually do this setup in the lab, and we could look at the phase noise of the oscillator. And then and we can see how that phase noise changes as we convert the frequency eventually up to the stage when we can actually get up to the carry frequency. And then in our early work here, we looked at a few of the oscillator setups. So the radar oscillator is the one which we moved out into the lab here. See whether I can deal with the mouse here. So this device here, we call it the OCXO PLO, is actually a device which was the original native oscillator in the radar head. So we could measure this. We then actually was comparing with our photonics oscillator, and that has two outputs. One at the local oscillator of the radar, and with some experience, we found that wasn't the best output. So we were able to take one of the higher frequency output, which is actually at 1.25 gigahertz. And we found that was that device's best performing phase noise characteristic, and we could then have built up a bespoke converter. In this case, it was dividing that with local oscillator. Now, this is a little bit around with it, because we send this down, convert the signal to the radar, and then the radar timing waveform generation up conversion. But that's the setup we have, because that's some of the limitations we have having a COP system, because we have less access to the front end. So we limited what sort of changes we have. And then in this work here, we also compared to a Leo Bodnar GPS display oscillator, which had a very low performing oscillator. Here we've done the measurements of the phase noise at the local oscillator, but for reference, I've up converted to the carrier frequencies of the radar. So this is what, if there was no additive phase noise in the up conversion, this is what how the oscillator was compared. And what we can see that the manual one here is then giving us indeed lower frequency as low close to the carrier. Far out here, the conventional oscillator and the manual of photonics is giving similar one. And then the GPS display oscillator has a higher phase noise throughout this region here. So these are measurements we've done in the bench here. So we've got some understanding how these oscillators will compare. with and then at the same time, and it's Darren's been talking a bit more. If you have pair of these oscillators, what's the longer term stability? And here, an earlier analysis in the lab show that the free running oscillators will drift over time, so the Allen deviation will increase. A GPS oscillator will lock through GPS, will maintain stability. What the stability you can get from Menlo here will be much more higher. And I think, I'm not quite sure, what they're locked in this case or what they are free running.
This will be the
free running. So even when they're free running, the drift is such low that they are. And then what which Darren has done, he has actually now been locking one Menlo, so one cavity is then driving two of the devices where we're getting the optical to RF conversion. So having done that and said that we can actually see the difference in various oscillators, we then move to installing this interface into the radar here. So that cabling here, we then connected the radar into the cabin. We installed the oscillator in the cabin. We put the switch in there. And in this case here, we had by this time we have brought in a number of other oscillators into our assessment. So we acquired two of these here, which are Raycon built. These are German-based companies. They produce very high-end oscillators, which are highly stable. They have very low phase noise, close to the carrier frequency. And we have actually installed these in the radar cabin, tested them with the system. These two devices, the Raycon one again, produce only 10 megahertz output. So we had to put these multipliers for them one. So just like with the Menlo, where we had a higher frequency, put a divider to come down to the local radar low frequency. For these 10 megahertz oscillator, we put multipliers in there. Again, these are the ones that we built bespokely, and we can then get to the LO, and then the rest of the setup the same way. We can get the radar to generate a carrier frequency based on different oscillators. This whole setup we can actually control it remotely, so we can control the remote the switch remotely. And we can swap over between different oscillators. We can enable the radar operating, and we also put in a phase noise analyzer in the cabin. So for each time we do a measurement, we can then remotely refresh what the phase noise is, if there are any changes in the data. And that's the process we repeat for each of the trial here when we collecting raw data. Just to show you how these compare. So these are now phased out mainly within in the radar cabin with these oscillators set up here. We can now show that the blue curve, which is the Menlo, is start off with low phase noise close to carrier here. When it gets to about 300 hertz, then the radar on local oscillator, which is the green curve here, begins to be on par with this one. The Raycon one are interesting. There's the gray and the black curve. They at the lower frequency are similar to the Menlo, okay, but around about 100 hertz here, they actually flatten out a little bit. And then the GPS discipline oscillator is the one which is higher, and then far out, it's actually gets even better in that regard. What we have found, one of the things that here we have measured the phase noise going up to 1 megahertz. But in the radar here, we find that there's a fold-over effect which happens. So that when we take the oscillator phase noise, the actual the PRF is 7 kilohertz. The phase noise wraps around, and so what we find is that the far out phase noise starts getting lifted up. So what we find is that what an oscillator may close in may look good there. By the time you include the far out phase noise in performance, and we've noticed that in particular with the Raycon oscillator, that although they have low phase noise to begin with, and the far out wrapping around, they mean that at some stage they're actually getting worse than the GPS discipline oscillator. The Menlo stays on par with the PLO. Okay, but in this example here, I'm just showing the Raycon here and the GPS discipline and the PLO here.
So fundamentally, we can see across the red, blue, and green lines at low frequency offset, slow moving targets, you get tens of dBs more sensitivity with the clocks that you would recommend.
That's right. Yes, that's right. Okay. And what we've done here is we've done some radar trials, and I'll show you some earlier work. We've got some more results more recently, which we hope to publish soon. And in this earlier, so we're looking at strong targets. We're looking at their return. So, for example, this is a range of a map for one CPI. And what I'm showing here is as a function of Doppler and range what is the return looking at. And you can see that there is some region where the background is being lifted up, and that because there's strong clutter at 0 Doppler, and the phase noise is letting that background be lifted up. And the marker I put on there, which is at where Y is 18, is the location of that building power constraint. So that's a strong building, roughly about 1 kilometer, which has got some strong clutter return, and at that location we see the background lifting up. If you go away to a range where the background is clutter is weaker, the background will be lower. And what we then do is we now take the radar measurements and look at that particular location and then plot the Doppler response like you would do as a phase noise measurement. You can begin to see on the one-sided response that and now I'm only showing it up to 100 Hertz, that when I get to about 100 Hertz, I can begin to see tens of dB difference in the background level based on the oscillator correction. In this case, the best oscillator here is the PLO, radar on oscillator, and the others as well. But what was quite revealing for us when we did this trial was the Raycon, which we spent thousands of pounds buying, was no better than this setup, an oscillator which we picked for 150 pounds. So you have to be quite mindful. You just something is expensive, not going to do the job for you. So you have to be careful and assessment how the radar is going to take in that signal. So this is kind of the tools we have now. We have a radar which we can operate. We have a means to connect it to oscillator. We have a method where we can assess the real environment and look at the character of the oscillator and begin to relate to the performance of the radar. And that's going to be we are quite excited about, because that gives us a real means of seeing how the design, the work coming out of the colleagues with the physics about these high performance oscillators, how that's going to and what we're interested in is continue to benchmark this on conventional oscillators. This is the work we did in UCL. Their piece was quite valuable to us.
Yeah.
So and this is just an example to say that over the whole scene here, how much difference in dB level between the worst performing and best performing. So the green is saying that I can get up to 10 dB reduction. So you can see wherever there was strong clutter return, I'm getting up to 10 dB reduction in the background level, and therefore it increases the sensitivity. And that is the kind of level of understanding we want to get over the whole scene. And having a system which can look at a wide range gives us more assessment in this. And that's one of the strengths we have. So that's one of the reasons we went for a system to give you a wide field of view.
Was that two temporally separated measurements with different clocks?
Yes, that's right. Okay.
There is a time difference
There's time
between
difference,
them, but
that's
assuming the clutter was
yes, that's right. So some of these measurements we're doing at night time. So we were quite so some early measurements. All these measurements we done at night time. So the environment is quite fine, but they are temporarily quite different, because only doing 10 minutes of measurements and then stopping over the oscillator, and we can reduce that time even more. The bistatic measurement we do, they are temporarily the same, and they'll be more interesting to compare, and then Darren is going to show them. This is just to view that. So we have got a very complex setup here. So we've got two radars here. We have means to connect them to the Menlo here. They are now being connected to fiber net, both between the two radars and between the clock lamp. We now have a data storage server where we can actually store several tens of terabyte data, and that has been quite valuable, because our main benefit, because this radar has 64 channels, we generate about a terabyte of data for every 2 hours of raw trial video, and typically our trials tend to be between 1 to 3, 4 hours. So it's quite data intensive. Okay, I will kind of pass over to Darren at this stage, and then he's going to go a little bit more into network main trials and main.
Okay, thanks a lot. Yes, I'll go through the work that we've been doing with the UCL oscillators. I'll start off with just a short overview of what these oscillators involve. Then I'll be going through the frequency stability measurements, and we're going through the radar interface, how this is actually going into the radar setup, and then I'll finish off with the radar trials and some results from those. Yeah. So, of course, the UCL guys will know more a lot more about this than I do, but this is the RadSync device that they kindly loaned us for 3 weeks to do some measurements in collaboration. So this is this little like rack unit type setup.
Yeah.
Contains 2 GPS disciplined oscillators, one of them being the Thunderbolt E, which is oven controlled crystal oscillator disciplined to GNSS, and then the other one is the LNR clock, rubidium based oscillator disciplined to GNSS. So that is the that's in that one, but we've also included this one in the bottom left that I'll be using just for comparison. This is totally separate device. The one that was mentioned is the small 150 pounds Leo Bodnar GPS disciplined oscillator.
Yeah.
So it's low cost. It contains an internal TCXO and PLL for locking. So all these 3 GPS disciplined oscillators, we've been just doing some radar trials with these and comparisons and seeing what is the comparative radar performance. So I'll start off with the benchmarking of the oscillators. So we do some frequency stability measurements. Mainly, number 1 is being the what is the phase noise. So measuring the measurement of the short-term stability. This was done by measuring at various stages in the radar chain, and used the Roden-Schwarz phase noise analyzer to complete these measurements. See my notes here.
Yep.
And number 2, we've been doing we've done some Allen deviation measurements, measurement of the longer-term stability at 10 megahertz. The setup involves a K plus K frequency counter, which allows us to simultaneously measure all 4 channels simultaneously. And just so happens in these trials we have 4 oscillators, so this is the setup we used. One non-ideal, I think in retrospect, I think I would probably do it slightly differently, is that we have this 1 GPS antenna going into a splitter, so the same GPS signal will be going to all 4 of the oscillators. So that's just one thing to note. But on to what we learned from these measurements. So we're going back here to the radar chain that Jahangir showed earlier. There is a slight difference here with the multiplayer, but we're starting off at the start of the chain where we have 10 megahertz signal. So what we have is all 3 oscillators, Leo Bodnar and an clock Thunderbolt E, phase noise of the original oscillator before entering the radar interface. Several things we can see from this is a significantly higher phase noise in the Leo Bodnar, especially at the lower frequency offsets. Close-in phase noise is very high. This is determined by the internal oscillator inside. It's more it's a poor quality oscillator. And that's one of the main reasons we were interested in doing these measurements with UCL. Another one is you can see the white phase noise floor where it flattens out here. The LNR clocks are very low, down at minus 165 dBc per hertz, and this helps with the reducing the overall phase noise floor of the radar. Thunderbolt E is somewhere in the middle. Actually, the close-in phase noise, it's very low. Then we get a raised white phase noise floor up here. Another thing to notice is you'll notice the LNR clocks are very similar. Their phase noise performance was very similar.
Consistent.
Yeah, but we did notice that one of the Thunderbolts just had a few dBs extra phase noise. I won't talk too much about that from now on. We didn't really do much investigation into that, but yeah, just keep that on that. So this is the next stage. So this is after the first multiplication stage to get to the local oscillator frequency. Now all the oscillators we're comparing at 62.5 megahertz. The Leo Bodnar, we haven't multiplied this one because actually we do use this oscillator at 62.5 megahertz. So, but they're all.
Can you pick in 62.5 because that's the input to your sensor?
Yeah.
It wants to be run on that frequency.
Yes. Yeah. So we need to make sure we get everything to that frequency. So that's what,
Stage 1.
Yeah. So again, similar trend with the phase noise. But the only thing is because we're doing an up conversion, it's brought everything up.
Yep.
that's just fundamental. Like if we have some phase error, we're going to multiply that as we increase the frequency. Again, this is actually now after the third stage of multiplication. So now we've gone through, and now we've gone through this twig board. Now we're at probe C. This is all at the carrier frequency of the radar. So again, similar trend, and everything's being raised up, but now there is kind of less of a difference between each of the oscillators. But we still do see that the NMR clock is a good around 10 dB, maybe a bit less than 10 dB in some places. Okay. And as Jahangir mentioned earlier, what we've done is try to predict the phase noise after the aliasing contribution. So as the radar's PRF is actually at around 7 kilohertz, that means that this, if I go back, the phase noise here in the kind of tens, hundreds of kilohertz region is going to be wrapped around hundreds of times. So that's actually why we're seeing that such a significant raise of the noise floor, especially in the case of the Thunderbolt, where we had quite a high frequency phase noise. Just to add this one, so this is the Allen deviation measurements. So we have the we're comparing here the Leo-Badnar, the LNR clock, Thunderbolt. The short-term stability as we'd expect in this order: Leo-Badnar, Thunderbolt, LNR clock. And then in this measurement, we see that the two GPS system oscillators are performing much better than the Leo-Badnar. But as I mentioned earlier, there is a slight difference in the measurement. Take that with a grain of salt. So actually, the GPS inputs would be correlated. So it might end up being, it could be higher than this. That's just kind of a lower measurement here. So the next step is just describing how we're actually integrating the UCL oscillators into the radar system to do the measurements. So very similar to what was shown earlier. The oscillators would be here at the start of the chain, two of them in each radar, going into this RF switch. RF switch here is allowing us to remotely switch between the two oscillators during the trial. The big difference here is that the multiplier is placed after the switch, because we're using 10 megahertz oscillators. We want to bring them all to 62.5 megahertz. So yeah, that's placed there with a bandpass filter here at 10 megahertz. But after that, everything is similar to what we've seen earlier. So there's the low phase noise buffer, and then the twig board bringing it to the carrier frequency into the rest of the radar chain. So here I'll just show quickly the what it looked like after setting up in the radar. So this is in GK0. We had some space in this area here. This was actually before we delivered in one of the atomic oscillators, so we had that space available. Whereas in the other radar, we didn't have that space, so we placed it on top of the server rack here. But in fact, in case of the actual RF chain, so it's the same. Okay, so now I'll be going through the bistatic drone trials and their results. So this is an overview of the setup we had. So the two radar systems. One is on top of the ERI building. Another one is here on top of the Gisbert Cat building, with a baseline of around 180 meters. We operate in bistatic configuration during the trials. So we have these two different configs. One of them default config. This is just the standard operation where one radar will be both transmitting and receiving. This is how the radars would usually be were designed to operate in. The other config is the RX bistatic config. Here the transmitter power is set to 0, so it's now receive only, and it's depending on the transmit signal from the other radar to make its detections and receive low static echo. Everything else is the same, except for actually the recording window is slightly extended to try and receive the direct signal. So during the trials, one radar will be set to the default config, and one radar will be set to the RX bistatic. We can maybe swap it around. And also we do both. Sorry, it's been yeah, we do maybe a few flights with one configuration, then swap them, do a few more flights, and so on. The radar trials themselves. So we was able to do 3 sets of trials using the UCL node. In 3 locations. So these are the 3 locations. First one being the Vale site, and the Richmond site, and the next one Pitches site. Each site had one flight pattern. Where we, for example, launch at one point, and then we go through these preset waypoints, so we can get kind of repeatable flight paths. So yeah, that's the same for all 3 of those. The drones in question here, we have the DJI Inspire 2 and the Trees. These are the bigger drones, and these are the ones that are able to do kind of autopilot. They can just go straight through each of the waypoints, so they're very repeatable, as you'll see later. The DJI Mini, this is nice as it gives us a very small RCS target to look at. However, we can't do this. This is a manual one, so someone has to fly this. Usually, or Dan has to fly this manually. Sorry.
Less repeatable because it's not waypointed.
Yeah.
That was the case. We now actually managed to fly that through waypoints as well. So we're getting repeated with that. But previously, yes, so it's less repeatable, but it does give some lower signature.
Because it's the smallest.
I've also included one. Oh yeah, so I just mentioned we had during those 3 trials a total of 48 geometry flights and multiple hours of raw data, so a lot of data to work with. And I've also included one trial here, which was from before. This was back in October time when we used the Leobot oscillators and flew around Richmond with the Inspire drone. So the bistatic trial analysis will be performed, that I'll be showing in my next slides, focused on 3 key areas. So one of them being the bistatic synchronization to try and measure what level of synchronization we have achieved here by measurement of the phase error using the direct breakthrough signal and measuring the unwrapped phase. Then comparison of the phase spectral densities using that same phase signal. Second is looking at the actual effect of the phase noise in the urban environment. As mentioned earlier, we're going to see what that has an effect on the background noise floor using the different GPS spin oscillators. Then finally, we're looking at the target detection, seeing what the spectrograms look like, and doing a quick SNR comparison. And these are some photos of the during the trials. Oh yeah, these are the 3 locations all on the same map. So they're all kind of in the 1 kilometer range. Okay, now firstly on to the timing error. So as I mentioned, we collect we point our beam towards the direct signal and try to collect the time series data, which contains IQ data, so we can extract the phase information, unwrap the phase, and what we see here over what I'm calling the sub CPO phase errors, so only in a 2 seconds time period.
Yeah.
The behavior of each oscillator is very different.
Yep.
So we have this red one is the Leobot. Seems to have this kind of oscillation, correcting and then correcting back. So in this plot, we always see an oscillation.
Is this phase error measured on a strong target, or
So this one's measured on the direct signal itself.
Direct signal itself, okay.
So that's yeah. All of these are when, for example, both radars are used in the Leo Bodnar, we extract the direct signal.
In a way, I guess phase error, you know, quite different category, order of magnitude differences between each one. It's like a nice result actually to show what you get for your money. But in a way, perhaps even variability of phase change, almost like the differential of this is another piece as well. If it's pretty steady, maybe that's correctable, predictable, handleable. But if it's very variable in its own right, that's even more of a problem, perhaps.
Yeah. So this is just one CPI.
Sure.
But if I do multiple CPIs, which I've done, you get different numbers. But the magnitude should be similar.
It's these three.
Correct. So we get like hundreds of picoseconds for Leo Bodnar, tens of picoseconds for Thunderbolt E, on the order of picoseconds for the LNR clock.
Okay.
Yeah, so here I've just converted phase into time error rate at the bottom. Now we look at the long term. So if we decide to extract a long 30 minutes of time series data, measure the phase, unwrap the phase, we get kind of this plot. So this is the surprising thing is that here the Leo Bodnar seems to, on the longer term, seems to correct, seems to stay very close to zero. It seems to keep correcting back. So we had these shorter term oscillations, and we have actually a longer term another oscillation in here. We have the so what we can see is the Leo Bodnar has a lower timing error over the long periods of time, but it's actually a lot worse over the typical CPI lengths that we tend to deal with. We're also comparing the LNR clock and the Thunderbolt T. The LNR clock is actually more smooth. You can see it doesn't have so much variation on the short term, but it does. It seems to have drifted off at this point. The Thunderbolt E, we noticed, tends to have, sometimes it would have a higher gradient, which would represent an off, kind of a frequency offset. Probably not a large offset, but maybe a few 100 millihertz offset or something could cause it to have this type of phase gradient. But it does end up trying to correct back. And in the end, we do get something that's a bit closer to zero. Onto the measurement of the phase period spectral density. So we get the same phase, and we get a few seconds of the phase data to measure this one. You see, looking at the different noise processes that we have there on the direct signal, and we get similar story to what we've seen in the phase noise plots, where the close-in phase noise dominated in the Leo Bodnar, and the high frequency phase noise dominates in the Thunderbolt, and again LNR clock has lower phase noise at all frequencies. Quite a significant difference there between the Leo Bodnar and the other oscillators. Okay, now on to the second part where we're looking at the effect in the urban environment. So as Jahangir mentioned earlier, looking for a piece in a part in the kind of a field of view which has very high flutter. I've actually chosen a different one here. This is the Tri-Gate building. It's around 4 kilometres out, and it's kind of this corner-shaped building with just a very massive surface area, so you can see it's a very high peak at the far right range. So we get raised noise floor in this region. So I measured the background noise floor over 2.5 minutes of data. So I do this to try and average out if there's any targets in the data, try and average those out. So we should be seeing actually the noise floor.
Is it a noise floor or is it a cluster response?
I think it's more cluster response, I would actually say, because basically at that stage, we are not seeing a thermal noise floor anymore.
That's that large building's response. But averaged over a long period of time to smooth it, ensure there's no moving or variation. Thank you.
Yeah. So in this case, because we're looking in that area, it should be just phase noise. So we should see how much the phase noise is limiting us. And again, we can see I've put in a higher CPI here and kind of zoomed into our area of interest. So we've only gone up to 90 hertz each way. This is kind of typical frequencies that we would spot drones in the ones we're interested in.
Okay.
And here we can see the LNR clock has about 10 dBs difference at most frequencies in this area of interest. So this would demonstrate a kind of reduction in the phase noise and increased sensitivity in this particular region. Now on to the target spectrograms. So here I'm just taking an example of monostatic and a bistatic. So of course we're running both of them at the same time, both radars recording at the same time. So this is kind of a demonstration of how using this Leo Bodnar oscillator. The oscillator instability is kind of exposing itself in the spectrogram here as increased phase noise. And as you'll see,
there's a Leo Bodnar in both radars.
Yeah. So for all of the measurements here, we try
matched clocks.
Yeah, matched clocks in each radar.
Thank you.
Here, what I'm doing here is it's the same. I'm just zooming in and I'm showing the detection. So it's showing where there is a right side detect, where it's a misdetection, which So so it's an increased phase noise, and there's actually these fluctuations in the observed target velocity. This is matching actually the behaviour of the phase. It's kind of oscillating around. Actually, the frequency is kind of moving back and forth, and that's kind of showing in the spectrogram here. It's actually the cluster itself is oscillating. The target is oscillating. The spurs are oscillating. It's so that's kind of one. That's something that you get from this phase oscillation. So now on to the target spectrograms with UCL oscillators. So this first one is the one I showed earlier, the Leo Bodnar, just for comparison. And now I'll show the same. So this is actually the same location, same radar, same drone target, same altitude, but we now have just a different oscillator in the two radars, and it is at a different time than this one, because they did this one at an earlier date, the first one. But other than that, everything is quite consistent, and you can see just how, well, you'll see more in the next slide when I compare the flight patterns. They're very repeatable.
Yeah, that's
like the time it takes for it to reach from one waypoint to the other.
yeah, the pattern's very.
There's a bit, but at least we can kind of match them all, align them all to each other.
Yeah.
But this is the Thunderbolt. You can see this compared to the other one. You can see a much lower noise floor. The clutter isn't spreading out as much, and we have fewer misdetections, because especially in this region.
And these tram lines that were present here aren't present.
Yeah.
In that case.
Yeah, that's another. Yeah, that's for some reason the Leo Bodnar seems to have a lot of spurs. That's what. And in the bistatic case, in the monostatic radar, they're not too bad. In the bistatic case, if they've got different.
Those static cancellation not taking place, and many of these spurs, which is sort of artifacts, maybe sometimes, and they are actually related to the flutter. So where there's strong flutter, you actually see more of those than you see.
Yeah, perfect. Thank you.
And if I show the next one, okay, this is the LNR clock. So we can see actually now the spectrogram looks a lot cleaner than it did. It's like progressively better. Again, with the same flight, it's a bit shifted. I think from my start time.
Is this another target like a bird in the scene?
No, so that's the harmonics of the drone here. So these are home lines. Okay. But if there was another bird, that will move, but then that won't.
It wouldn't be correlated with the movements of that.
So that those are characteristics of that.
Okay.
Why are you seeing those more in that last plot?
There is, I think, for some reason the axis is extended here. see the x-axis here is a bit further down.
Okay.
So it matches here, but I think what's happened is the blades have kind of covered the same bit. I think that's what's happened there. In the top one, the noise floor is increased, so it's kind of masking them. In the bottom one, it seems like each of the four blades.
And in fact, these blades are quite good because here the target is quite strong. We are sitting around about 50 dB SNR. So it changed a little bit of background noise. But we do notice that if you look at now the home lines, because they're about 15 dB lower, any drop in the background level will make them more visible, which you can see them in the lower bottom. So now the SNR on the home lines, you can actually see that they are, you get a lot more detection of them. Whereas the top one, it's probably hard to get any.
Just one more slide here, just showing the SNR comparison. So all those free flights just plotted here, the signal to noise ratio that we've measured from the free flights respectively. And one big point here is the Leo Bodnar has this very significant reduction in SNR. But actually, there's more than there's actually something that is causing that. As you mentioned earlier, the Leo Bodnar has these two spurs inside, and unfortunately, the flight. The velocity of the drone is matching.
Sits on them. Yeah.
So,
Yeah, right on that. Yeah.
So that's why it's like 30 dB the difference here. It's to note that the noise power is calculated using the average statistics in the same range of Doppler. So if there's a spur there, it's going to raise the noise. But overall, you can see that throughout the entire flight, the signal to noise ratio of these two GPS system oscillators are significantly higher, around 50 dB SNR, increasing above that. And I think it's cut off at the bottom, but yeah, it's showing how repeatable the flight is. We compare the velocity against the flight, and see, especially during this first part, they're all
Overlapped trajectories or something.
Yeah. So just to summarise, on the quantum-enabled radar testbed, working on creating the world's first experimental facility powered by quantum technologies operating in the urban environment. Developing bistatic, multistatic system concepts for detection, location, and tracking. For the network synchronization, UOB steering radar was able to operate with the UCL supplied high-performance GPS system oscillators and demonstrated successful synchronization. As you see, the LMR clock seemed to be superior in most of the metrics we were showing throughout the slides. As for the future work, we're going to be looking at trying to operate our network using these photonic oscillators I mentioned earlier, one in the free running case, and another one where we're trying to make use of a fiber link between the two radar systems and send kind of the same both frequency codes to the same kind of cavity, and measurements in the lab show that we can potentially get something along this order here. But in other works, there's also work in trying to look at other ways of synchronization of the network through post-processing. So this is something that hopefully will be coming out soon. It's got some kind of promising results here. So overall, the November trials in collaboration with UCL are providing a valuable benchmark for baseline network performance with the conventional technologies. So thanks a lot for everyone involved in that. Just one more slide here on the team involved in the trials. So on the engineering side and the physics side here, led by Mike Antonio and Yashpal Singh respectively, and various other people working on multiple areas really. And that's it. Yeah.